Let us move now to the fifth step, in other words, the modeling step. And our aim is to construct a mathematical description that is able to, in other words, a model that is able to reproduce the experimentally observed characteristics of viscoelastic material model. And for this, we are going to look at combinations of the fundamental rheological elements which together eventually yield a suitable model. So we're going to propose combinations and we'll see if these combinations are viable options. So obviously we are working with the fundamental rheological elements, and the way we combine them, it's either going to be in series or parallel or some combination thereof. So what we have, first of all, let us go back. If we have a single spring or a single dashpot, that's either a pure elastic solid or a pure viscous solid type behavior, and that is not what we want to have. We want to have a combination of these two behaviors. So the individually they don't work, and so my choices are, well, why don't I work with combinations of two? So combinations of two, you take them either in parallel, which is what we did in our previous slide. So that's one model. Again, this is not a structural model. Always remember, these are things to remind us of how to construct the corresponding material model. Okay, so it's a material behavior and material parameters that eventually that are eventually implied by these individual elements, and their combination is going to be an individual viscoelastic material model. So here, that's the first combination. The other combination, obviously, is a series combination. So here you're going to impose either stress or strain as a function of time, and you measure the other one. If one is a constant, then the other changes over time. You have either a creep or relaxation type material behavior. So now these combinations, by the way, are so important that they have special names. This one is a so-called Kelvin model, and this one is a Maxwell model. Alright, so, well, let us question whether these models are viable options. So our idea is going to be based on whether they can reproduce fundamental creep and relaxation or relaxation behavior. So we can, of course, look at both of them, but ultimately let us just make sure that if it is a good model, then it should satisfy the type of behavior that we expect under creep and relaxation experiments. So the left picture here, remember from the previous slides, the creep, the right one is the relaxation experiment. On the left, stress is a function, strain changes over time. Let's just show that portion. On the right, strain is a constant, stress changes over time. So now that's what we expect, and these are the models. So I'm going to discuss this qualitatively. Of course, you can put the model explicitly, write it out, and work with it quantitatively, let me say, but it's sufficient to discuss at this stage qualitatively. And we'll validate or disvalidate whether these models are good or viable options for modeling viscoelasticity. Let's start with the Maxwell model. The Maxwell model. So after a single rheological element, combinations of two. It's one of the two possibilities. The Maxwell model is such, and now I want to look at the particular situation where we have a creep experiment. And on this, I impose a certain amount of stress, and this is how I expect the strain to change. So I impose a certain amount of stress. What I observe is that the strain should eventually change gradually, but eventually lead to a finite value. In other words, under the action of a constant stress, the strain does not increase forever. It eventually saturates to the limit of a material that acts like elastic, just stiffer than the original elastic behavior. And then I look at the Maxwell model. there is in this thing a dashpot that is free on its own in series with a spring. Now, these are material models, but if you like, think of them as structural element combinations, a structural model, if that's going to help you. So, for instance, if you had a bicycle pump connected to a spring and you were pulling on it with a constant force, well, what we expect is that this pump, the handle of the pump, will just move forever. If the pump itself is sufficiently long, it will just move forever because the pump is sensitive to the amount of force you apply. The higher the force, the faster it deforms. Or if you want to deform it faster, you apply a larger force. In any case, if you apply a non-zero force, the pump is going to just elongate forever, or it's going to get compressed forever if, again, it is long enough. So the amount of strain under the action of a constant stress is not going to reach saturation, but it will go forever. So therefore, I can conclude that the Maxwell model is a good attempt, but it's not a good enough attempt. Similarly, if we look at the Kelvin model, and this time what we can essentially look at, well, you can always look at either one or the other material model, but let's look at the relaxation experiment. In the relaxation experiment, at time equals 0, you impose a certain amount of strain, you suddenly pull on the material, and you expect the stress to jump like this to a finite value and then relax. Okay, so let's have a look here. You have a dashpot and a spring. You extend it at time equals 0 by a finite amount. You pull on it through a certain strain. So time equals 0, there's a sudden jump. Well, quick question. What is the rate of strain at that moment of sudden elongation? So think about it for a second. So there's a sudden jump. What is the rate of the strain? The answer lies in that picture. The rate of the strain is the slope of the red line. Here it's 0 because it's a constant strain, but here the slope is vertical, it's infinite. So the rate of strain is infinite. Okay. So when the rate of strain is infinite, the stress contribution to the overall stress that you measure here from the dashpot is also going to be infinite, because stress contribution is viscosity times the strain rate. So therefore, the stress jump that you have here, it's not a finite amount. It's an unrealistically large, in fact, an infinite amount with the prediction of this model. So we disvalidate this model as well. It's a good start, but it is not a good enough start. Okay. So it seems, therefore, that we had combinations of the two possible combinations, they just didn't work. So we go to the next meaningful step, which is we look at combinations of 3. Okay. And combinations of 3 can be cast. Well, there are 4 possibilities. There's going to be 1. We can take the Kelvin model, and to it we can add a dashpot in series, or you can take again the Kelvin model and you can add a spring in series, or you can start with the Maxwell model and you can add a dashpot in parallel, or you can start with the Maxwell model, and you can add a spring in series. Now, first you might ask, why only those 4? Why don't I take a Maxwell model and not add something in series? Well, because if you add a spring in series, the 2 springs would effectively act as 1 spring, or if you add a dashpot, you would effectively have 2 dashpots acting effectively as 1 dashpot. Now, similarly, if you go back here, instead of adding something in series, if you want to add something in parallel, if you add a spring, you can combine these 2 into a single spring. If you add a dashpot, you can combine those 2 into a single dashpot. So these are the only 4 meaningful options. Everything else is sort of irrelevant, or let me say it is a model that would be equivalent to the original combinations of 2 with just updated constants for springs and dashpots. So these are the 4 interesting models to look at. So now, by the same arguments that we made before, first of all, if we ever have a dashpot by itself in series with something, it will essentially creep forever. That was a problem with the Maxwell material model and viscoelastic model, and therefore this one is also disvalidated. And alternatively, if you have a dashpot by itself in parallel with something, at time equals 0 in the relaxation experiment, the amount of stress you have to impose for a finite constant instantaneous strain, it's infinite, which is also unrealistic. So a dashpot by itself in parallel is also not something you desire. Now it turns out that the remaining two models are actually models which predict a stress-strain relation in time that are qualitatively similar to the type of behavior you expect in viscoelasticity. Okay? So these two are actually viable models. Again, are the crossed ones not viscoelastic material models? They certainly are. They display viscous and elastic material behavior at the same time. It's just that it's not the type of behavior that we typically observe in with experimental measurements. So these are the ones that are able to at least reproduce those results qualitatively. Are they very good models? No. It turns out that they are not good enough, but still they are the first two models that are viable options for modeling viscoelasticity. Now, the one on the right is typically what one understands when one says a SLS model or a standard linear solid. That's the name that's typically is attributed to this setting over here, SLS, the first three letters. And that's the way I'm going to call this model, SLS model. This is also another model, but the one that we're going to analyze is this particular setting. Okay, so we're going to go ahead and concentrate on the standard linear solid model. That's what we're going to call this. And from now on, that is what we will concentrate on. That's what we're going to build on. And we are going to show that first, it's going to display the type of relaxation experiment behavior or data that we observe. Okay, so it behaves correctly under relaxation. It turns out creep behavior is also correct, but we're not going to analyze creep. So next we jump to relaxation.